Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to lecture number 5. So, in the previous lecture, we discussed topics related to power and energy, and we were trying to solve this numerical example, the one that's in front of you right now. The numerical example has given you the graph of power consumed in a house with respect to time, and the time is given in hours. So this is midnight, and this is also midnight. So these are 24 hours, and in between you have your midday or afternoon. So this is how a house is consuming power. Um, and we are asked to find out the total energy consumed in kilowatt hours and the average power that this house is consuming every hour. So you can see that the power is moving up and down throughout the day, and we are being asked to give us an average value. If that were consumed, then the power would be uniform, and the total energy consumed would be the same as this graph. So in part 1, we need to find the energy consumed for the whole day, and in part 2, we need to find the power that is representative of this graph that can be consumed on average throughout the day. So let's quickly start talking about this. You can remember from the previous lecture that we discussed that kilowatt hour is a unit of energy, and it's used commercially in our homes. The other unit is joule, but joule is quite scientific and much more harder to measure. Therefore, kilowatt hour is much easier and practical to use. And with this, we can measure the consumption of the house. So how are we going to do this? Of course, we need the equations to do this. And the equation here that is going to help us in solving this is the equation for power, which is power is work done per unit time, or energy per unit time. And in this equation, we can rearrange the terms so that we have dW equals PdT, and then we can apply integration on both sides from some time t naught to t1. So this is how you're going to write it. So the equation finally becomes uh, integral dw would become w with the range t naught to t1, and on the right hand side, since we do not know the function p, we can leave it like that, t naught to t1 p dt. And if we apply these limits to the energy, we are going to get energy at time t1 minus energy at time t naught is equal to integral t naught to t1 p dt. Now this is how we can solve, and I must tell you that this energy at time t naught is considered to be the energy when you were starting measuring the energy. And since we are assuming that before the midnight 12 a.m. here, before this point energy was zero, so we can put that over here, energy is zero, and the simple equation would be w of t1 equals integral p dt from t naught to t1, and this t naught is the 12 midnight over here, and this final t1 value is this value over here, t1. So this is t naught value, the time t naught, and this is t1 value. Now, I must clarify one thing, that if you are going to apply this integration formula You must be careful because again the function P is actually in is presented in this segment. It's different. The function P is different over here, the function P is different over here, and the function P is different over here, and finally it goes back to 2. So there are 1, 2, 3, 4, 5. You need to write 5 piecewise function pieces of this function in order to apply this integration formula. So this is one way of doing it. You can do it in just the same way as we calculated um, the current waveform in the last class, in the last lecture, where we formed a piecewise function for charge and then applied derivative to it. Uh, there is an easier method because you know that energy is the area under the curve of power. So we can easily measure the area under the curve of power over here, and you can see this is the area that we need to measure. This is the whole area, and since they are simple rectangles, we can easily measure W directly, and the W from time the energy, the amount of energy consumed between 12 a.m. throughout the day till 12 a.m. on the other day is simply going to be these rectangles. And let me just quickly start measuring that so that we don't waste time into it. You can see that this is one rectangle. So from um, 12 to 6, which is actually 6 hours. So the horizontal breadth is 6 hours, and the height is here 200 watt. So we need to perform we can say that 200 watts, the height multiplied by the base of this rectangle, is 6 hours. And since this 200 is in watts and 6 is in hours, the unit would be watt hours. Remember that we need to convert them into kilowatt hours. So what I need to do is I need to divide it by 1000, and that would make it kilowatt hour. This is the first part. The second part is going to be this bigger rectangle, the one with greater height, and you can see it's 6 to 8 on the base, which is 2 hours, and on the height it is 800 watt. So we can say 800 times 2 hours divided by 1000 to convert it into kilowatt hour. Plus, what is the next step? The next step is simply the power goes down to 200 watts, and this is the region. I'm highlighting that region, and in this region how many hours are spent? So 8, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hours are here on the base, and the height of this rectangular is 200. So 200 times 10 hours divided by 1000, plus this second last region. Let me pick another color for that. So this region over here, and in this region you can say 6, 7, 8, 9, 10. 4 hours on the base, and the height of this rectangle is 1200. So 1200 times 4 hours divided by 1000 for the kilowatt hour. And finally, in the very last region you can say 10 to 12. So there are 2 hours in this region. This is the very last region. So there are 2 hours with 200 watts. So 200 watts times 2 hours divided by 1000 to convert it into kilowatt hours. And when we sum all of these numbers, we are going to get the energy consumed between 12 a.m. the previous day to the 12 a.m. the current day, 24 hours. You can easily simplify that by taking 1000 as a common denominator, and the remaining would be 200 times 6, 12. So that would result to 1200 plus 1600 plus 2000 plus 4800 plus 400. And when we sum these together, we are going to get, so this is 12, this is 16. So what we are going to get is simply, uh, let me quickly use the calculator over here. So this is the sum: 1200 plus 1600 plus 2000 plus 4800 plus 400, and that results to 10,000. And since this is 10,000 and there is a division of 1000, I need to divide it by 1000, and the result is 10 kilowatt hours. So the energy that we have found between 12 a.m. Midnight to 12 a.m. midnight the other day, the final value of that energy is 10 kilowatt hours. This is actually amounting to 10 units of energy. This is how the energy company is going to bill 10 units, and whatever the rate of 1 unit is, they are going to charge you with that. The second part of this question is much simpler, and it's asking you what is the average power that the house is consuming per hour. So what you need to do is you need to find this some sort of um, average line through this graph, where if you use that amount of power every hour in the day, you would come up with the same amount of energy. And that is quite simple to do. You just need to use the same equation: P equals dW over dt, and here you can use the same energy that you have already computed. So P equals 10 kilowatt hours, and since the total time is 24 hours, the house was consuming energy for 24 hours. This was the energy consumed in 24 hours. You can divide it by 24 hours, and then what you are going to get is 10 over 24, which is roughly 5 over 12 kilowatts. This is the amount of energy, the amount of power that if the house was consuming every hour, the house would have consumed a total of 10 kilowatt hours of energy. So it's kind of the average power that the house is consuming every hour. In reality, the house is not going to consume a constant amount of power. Its power value is going to go up and down. So this is how we can solve examples of energy consumption in our homes and daily lives. This was one of the examples. We are going to do some other advanced examples later in this course when we talk about AC power. because this is the graph for AC power. We are not talking about that. Currently, we are studying only DC power, and later we are going to see what is the slight difference in alternating current power and direct current power. So for now, I think you get the concept of power consumption. In the remaining lecture today, I'm going to talk about the different kinds of circuit elements that we are going to use in this course. So let me introduce you to the kinds of circuit elements. So let me first put that into perspective for you. So we are going to talk about kinds of circuit elements. I'm just going to introduce you today to the different kinds of circuit elements, and throughout the course we are going to study them in detail. So the basic circuit elements that you are going to encounter in this course and in any course is the independent current and voltage sources. Now, I'm going to start with voltage source here because you are already very familiar with voltage sources. When I say independent, I mean that the voltage source has no controlling or no, you can say, restricting element on it. So for example, a battery, this is a single cell. So for example, this is a single cell of 1.2 volts, or you also purchase batteries. uh, Common batteries are carbon batteries, nickel cadmium batteries. A battery is a combination of cells. So these are several cells connected together, and they might be totaling up to 9 volts, for example. There is another symbol for representing these kind of sources, and they are, these are, for example, 9 volts. This is another symbol for representing voltage sources which are independent. So these are all independent voltage sources. What does that mean? An independent voltage source, well, let me explain this with the help of a graph. So this is the time axis, this is the voltage axis. So what's going to happen? An independent voltage source would have a voltage, for example 9 volt, and that voltage is not going to change over time. That's the idea. It's not going to change, it's constant throughout, and no influencing factors can reduce or increase that. There is another idea that I would like to discuss, that for example this is the graph of voltage with respect to current. And let's say on the voltage axis, since this source is 9 volts, so I'm going to draw that line. And on the VI graph, the voltage current graph, 9 volt source is going to look like this, a vertical line going up and down. And this graph tells us that an independent voltage source is uh, always going to give you 9 volts regardless of how much or how little current it's delivering. So the voltage source is going to keep on delivering 9 volts. The current would be depending on the kind of resistor or other devices that you have connected. Voltage is going to remain fixed. The current can vary all over the place, up and down. The voltage is going to be fixed. So this is how we define an independent voltage source, and the best example of such an independent voltage source is your battery. Now there is independent current source also. So a current source is given a symbol like this, And an independent current source, for example, it's giving you 5 amperes or whatever the current amount. An independent current source is a source that is going to keep on delivering the same amount of current for all time. It's not going to change over time. Now, this is a DC independent current source and just going to keep on delivering that amount of current. Similarly, an independent current source, when we look at its VI graph, so on the VI graph, then independent current source will have some constant amount of current, so let's say 5 ampere, and that current is going to remain constant regardless of the amount of voltage. Whatever the voltage is, we don't actually know the voltage around the independent current source, we only know its current. So the voltage can be just any voltage and the current is just going to be fixed. The voltage can vary all over the place. This is how an independent current source works. Now in real life, we don't really see current source examples a lot. There are very few current source examples in real life. And mostly the current source examples are very small. So in electronic circuits, you might find very small current sources of 10 milliamps or so, not larger than that. So you might not find them common in real life. So this is the independent voltage source here, and this on the right hand side is the independent current source. These are very common elements in circuit analysis. However, there is another concept of dependent voltage and current sources. So let me write that down. Dependent voltage and current sources. What are these? Now let me first show you their symbol. So their symbol is made up of a diamond shape like this. That's the basic idea. If that diamond shape is containing an arrow, this is a dependent. Sometimes dependent is also called controlled current source. And if that diamond shape contains polarity plus minus sign, then that kind of a source is called dependent or controlled voltage source. Now these are two kinds of sources that you are going to encounter in circuits, but not in this shape. Let me give you a couple of examples. You would get the idea here. So you have learned about transistors. Transistors are basically two types. There are two famous types of transistors. One is called the bipolar junction transistor, and the other is called the metal oxide semiconductor transistor. You are going to learn about those in your electronics courses. They have slightly different symbols as well. So this one looks like this, the other one looks like that. The bipolar junction transistor is, well, you can model it in such a way in this kind of a circuit that it has this current source in it, and that current source is actually controlled by the current going into the base of the transistor. So this is the bipolar junction transistor base, current going into the base. That base current actually controls the current flowing between the emitter and collector. So what the uh, what it looks like is there is some factor beta multiplied by the current IB, and that is the current flowing here, like that. So you can see what's happening. The current flowing into the base of the transistor is actually controlling the current flowing through the emitter collector path. The emitter collector path is current is simply a constant multiplied by the IB value. So this is a current source which is controlled by a current controlled current source. Similarly, if I talk about MOS transistors, metal oxide semiconductor transistors, they have a very different behavior. In a MOS transistor, one terminal is called gate, the other two terminals are called drain and source. This is not important for now, but let me just clarify what this transistor is going to look like in a circuit. So gate, drain and source. So what happens is that the gate terminal, this is the gate terminal, and this is the source terminal, and what happens is that the gate terminal is like this, and you can see this whole thing is the source terminal. So this is the S, and this is the drain. What happens is that whatever voltage you apply on the gate terminal is reflected over here by some constant multiplied by the voltage on the gate. So the voltage across ds here is a function of the voltage across gs multiplied by c. So what's happening over here is that if you apply a little voltage G here, 5 volts for example, then that voltage is multiplied by, for example, 10, and 5 tens are 50. So 50 volts are going to appear on the other side. And this kind of a device is called a dependent or controlled voltage source. And what is controlling this voltage source? Another voltage. How do we know that it's another voltage? Look at the expression here. It's C times Vg. The controlling parameter is Vg. C is a constant. The controlling parameter is a voltage. So this is a controlled voltage source that is being controlled by a voltage. On the other hand, for a BJT, this is a controlled current source that is being controlled by IB, which is another current. So this is a current controlled uh, current source. So this is how we are going to see these kind of circuits. These elements are also very common. For example, transformer. You know that there are transformers. You have studied transformers in your previous courses. A transformer is considered to be a voltage controlled voltage source. It can be modeled as a voltage controlled voltage source. We are going to see that in an example when we study transformers. So it's similar to this kind of a MOSFET kind of device. It's quite similar to a MOSFET. The only difference is in a transformer the controlling constant is based on on different things. On a MOSFET the the constant is based on some different parameters. Now the other kind of the other kind of elements that you are going to see in this course are, let me write them. So these are passive elements. Now you have already heard the term passive. We discussed the word passive in passive sign convention. You remember the sign convention for power, that power when when the current flows into a positive terminal, power is consumed and positive, and when the current flows into a negative terminal, then the power is delivered or the power is provided by that circuit, and power is considered negative. So passive actually means anything, any element that cannot deliver energy. So all those elements which cannot deliver energy are going to be categorized as passive elements. Let me give you an example and you are going to understand that. So for example, a resistor. A resistor R, let's say there is some voltage across it V and some current is flowing through that resistor I. So a resistor is such a device which is not going to provide you with any power. A resistor cannot provide you with any power. You understand that. It can only consume power in the form of heat, and whatever energy is given to it, it converts that into heat. When you use a practical resistor in circuits, you are going to see that the resistors usually become hot, and that is the reason that that is an indication that they are consuming the energy and just converting them into heat. They cannot store the energy, and they cannot a resistor cannot store. So I should write that a resistor cannot store energy, and the resistor cannot provide any energy. And since it cannot provide any energy, we call it a passive element. You know the equation for resistor. So the equation for resistor equals V equals IR according to Ohm's law. We have already seen this law. I'm going to discuss that briefly later in this course, but for now I think you understand the Ohm's law. The other passive elements, there are two remaining. So the other one is capacitor, C, represented by constant C. And let's say there is some voltage across the capacitor and there is some current going into the capacitor. So on the other hand, a capacitor can store energy. It can store energy for small periods of time, and remember that a capacitor cannot provide energy. So it cannot provide energy on its own. You cannot think of a capacitor that is running some light bulb continuously. It can store energy for a certain time and might light up any light bulb for a small time, but cannot provide it energy indefinitely, cannot provide energy for a very long period of time, and that's why it's a passive element. And the capacitor equation is, you need to remember these equations: I equals C multiplied by the rate of change of voltage dV by dt. And finally, the third element that we are going to discuss, well, you might be thinking about this equation. We are going to discuss this equation later. Finally, the third element in this course that we are going to discuss a lot is an inductor. And inductor is simply a coil, and it's represented by inductance L. Assume a voltage across the inductor V, just like a resistor, and some current going into the inductor. And again, the inductor is a device that can store energy for small periods of time, and it cannot provide energy indefinitely. It can provide energy for very small periods, but you cannot think of an inductor that's continuously giving you energy free of cost without getting charged. So inductor has to be charged, and then that energy can be discharged. Similarly, capacitor can be charged and that energy can be discharged, but the amount of energy coming in and amount of energy going out are the same for both capacitors and inductors. So even though they can provide energy for very, very small, brief periods of time, we consider them that they cannot provide energy indefinitely, and that's why a capacitor is a passive element. And the capacitor can then now it can then I can write the equation for capacitor as well. So the equation for inductor as well. So inductor's equation looks like this: the voltage is equal to the inductance times the rate of change of current di by dt. We are going to talk about this equation later. Finally, the very last point is that there are elements which are called active elements, and mind you, they are outside the scope of this course, but we might see a couple of them in this course. And these active elements are basically almost all of the active elements are made up of this device called an amplifier. An amplifier can be actually constructed out of all these elements, passive elements and voltage control, voltage source and other things. So an active element uh, is a device that can provide energy indefinitely, which means that even if there is less energy coming into the amplifier, it can amplify that and give you more energy on the other hand side. So it can provide energy indefinitely, and that is an amplifier. Now mind you, you might be thinking that if the energy coming in is lesser and the energy coming out is greater, then is this device generating any energy? The answer is, practically speaking, no, because usually amplifiers have separate power supplies from where they can get additional energy and then add it to the input energy. And when they add that energy to the input energy, the output energy can be greater than the input. So it's not a magical device, but when we are doing circuit analysis, we don't consider the energy taken from other sources. We just consider the energy coming in and coming out. And when you look at these two energies, you can see that this device can actually provide additional energy on the output side for a long period of time. So this was the brief introduction of circuit elements. Inshallah, in the next class, we are going to start talking about resistors, capacitors, and inductors and how they are used in different kinds of circuits. I hope you are understanding these lectures well. Um, you must remember that you are given an assignment for which I'm going to post an assignment in your Google Classroom about the documentary Shocking of a Story of Electricity. Please keep on watching that documentary. It's a very long documentary, I can understand, but it's very entertaining. There are going to be questions asked from that documentary in the assignment. So reminding of you of that. I think this is it for today's lecture. Thank you very much, and Allah Hafiz.